trigonometric integrals. Now, the basic idea here is the goal is that we're going to evaluate integrals of these different forms. So there's three different forms here. Basically, there are sines and cosines, and then tangents and secants, powers of those that are mixed together. And then there are cosines. There's cosines product, and then there's these right here where you're dealing with different constants in front of the x's. Okay, so and there's a bunch of useful formulas to do these. And so let's go ahead and I'll just show you some bunch of examples, but here are the formulas that we use for those. Okay, so let's go to the examples from the homework. Okay, so first one is evaluating this integral. You have sine to the 11th and cosine to the 5th. Okay, so now if this is the first case, this is the easiest case where you have at least one of these powers is odd. Okay, we'll say that's an odd power there. Okay, that's also an odd power, so you could do the same thing with this one, but it's easier to take the smaller of the odd numbers as a power. Okay, so what? So that's the key right there, that power is odd. And when that's the case, and you have sines and cosines, then what you do is you consider this, because the cosine to the 5th is actually cosine to the 4th times cosine theta, and cosine to the 4th is, right, this way, is cosine squared and cosine squared. And so then you write it like this: 1 minus sine squared theta, 1 minus sine squared theta. You change the idea is to change everything to sines, and then you have that right there. And I guess you multiply those two together, you're gonna get 1 minus 2 sine squared theta plus sine to the 4th of theta. Okay, so there's this right here, and we'll go ahead and plug that into the integral. So that pops in right there. And I'll explain, and maybe you see where this is going, maybe not. Maybe after this next step, you'll see where this is going. Okay, now if I distribute everything in, so I'm multiplying this times 1 times that, and I get that. Now this times this, the second term times cosine theta, that's going to be minus 2 sine to the 13th of theta, cosine theta. And then it's sine to the 11th times sine to the 4th is sine to the 15th. Okay, so what happened is now with each of these terms, we can conveniently use the chain rule. Okay, this first one right here, if you integrate that, it's going to give you sine to the 12th of theta over 12. Because if you take a derivative, you'll have a 12 coming down, and this will be reduced to sine to the 11th, which is right there. The 12 will cancel with that 12 that we have down here. And you multiply by the derivative of the inside, which is just cosine. Okay, and likewise this one, sine to the 14th over, it's going to be over 14, but there's that 2 there, so I'll just make it over 7. Okay, so now when I take the derivative here, I'll have a 14 come down. The 14 divided by 7 reduces to the 2, so that's where we get that. And then, of course, it kicks out the derivative of sine is cosine, which is right there. And then finally, sine to the 16th of theta over 16. Okay, and now it's going from 0 to pi over 2. Okay, great. So now if you plug the pi over 2 in, sine of pi over 2 is 1. So and 1 to the 12th is 1, 1 to the 14th is 1, 1 to the 16th is 1. So that's going to be 1/12 minus 1/7 plus 1/16. And then if you plug in, you subtract and plug in 0, sine of 0 is 0. So that's just going to be minus 0 there. And I worked it out on the calculator. The T84 is good to do this. T84 plus. Just put 1/12 minus 1/7 plus 1/16, and then press the math button and the fraction button, and that came out to 1 over 336 right there. Okay, great. So that's the first kind. Now let's do. So if one of the powers is odd, you can do that. Even you could do the same thing with the sine. If this one, you could like take the sine to the 10th. So this is the sine to the 11th is sine to the 10th times sine, and the sine to the 10th you can write that as a product of sine squareds, and then convert each of those sine squareds to 1 minus cosine squared, and then expand it all out and everything, and work that way, and use the cosine, use the sine as your. The sine would take the same role as the cosine. Okay, now if they're not here, if they're both even, like this case right here, that's even. So that's the harder case, and that's also even. So they're both even, and so that's gonna. So things are gonna be hard, but you use these formulas here, if that's the case. Okay, if they're even, then you use those formulas to reduce those, and it's gonna be the double angle. So so sine squared is this. So I'm just substituting there. And then cosine, this is cosine squared, okay? So basically cosine to the 4th will be all of this squared. Oh, dang, I forgot. We're dealing with t's here, and so I switched it back to x's because of the formula, but I should have left that as a t. Oh dear. Okay, so we have this is 1/2 squared, which would be 1/4, and this is 1/2, and this is 9. So we have 9/8 as the constant part, multiplied by, let's see here. If I multiply one of these with one of those, then I get 1 minus cosine squared of 2t. Okay, so one of those with one of those, but I have 2 of these. So I'm still going to have another one right here, like that. Okay, so all this thing is squared. I took one of them and multiplied by that, by this one to get this, because it's 1 minus a, or so it's a minus b times a plus b, and so it's a squared minus b squared kind of thing. And then the other one is right there. Okay, this right here is sine squared of 2t. Because 1 minus cosine squared is sine squared, but it's of 2t, right? And this is still 1 plus cosine of 2t. Okay, now this one, if we distribute this in, we have 9/8 sine squared of 2t. I can just split that up into two integrals. So I'm just distributing that in there. Okay, here I have a sine squared and I have a cosine. I just have a plain cosine to the first power, which is kind of what this is what we're shooting for, right? This one right here is sine squared. So that's just kind of, so for this one, I'm going to apply this formula again, okay, for that one. Okay, so that's going to be 1/2 1 minus cosine of 4t. So I get that. This right here, I can go ahead and integrate this. Because this is like, all this is squared. Another thing, I guess I should have maybe made more emphasis of, I'll do that. Instead of integrating right off the bat, I'll make more emphasis of this right now. That this square right here is really like as if you have this square right there, okay? So that's how you can write like this is the proper way to write it, but this is the proper way to think about it, okay? Okay, so now we can go ahead and integrate everything. So this is 9/8 and 1/2, that's got 9/16. And the integral of 1 is t, and the integral of cosine 4t is minus sine 4t. That's going to be divided by 4, because when you take the derivative, you have a 4 coming out. Okay, and then this one right here, this one is sine of 2t to the third power, okay, because the derivative of this will be cosine of 2t times 2. Okay, so if I take the derivative of the whole thing, I have a 3 coming down. So I'll get rid of that 3 that way. I'll also have a 2, and then this reduces the 2 right there. Then the derivative of the inside part is cosine 2t times 2. So I'm going to put a 2 right there as well. Okay, and then you got to put a plus a constant on the end. Okay, so now if I distribute everything in, I get 9/16 t minus 9 sine 4t over, 16 times 4 is 64. And then here this last term is going to be, the 3's will just, that will reduce to 3, so that's 3/16 sine squared of 2t plus a constant. Okay. I just forgot the shift key here, it looks like. Okay, so here equals. Okay, any questions on that exercise?
Yeah, on the sine squared 2t, is it not sine cubed 2t, or what happened to the cubed on that, on the?
You're right. Okay, that's sine cubed. Thank you very much for that.
Mm-hmm.
That's cubed right there. Okay, great. So let's move on to the next exercise, number 3. And here's where you have tangents and secants. Okay, so what you want to do is you want to move into a situation where you can exploit one of these two formulas, okay? So the derivative of the tangent is the secant squared. Okay, so the way that you can exploit this one is if you have an integral of, let's say, tangent to the nth power, but it's multiplied by secant squared, which is the derivative of the tangent, then that integral is going to be tangent to the n plus 1 over n plus 1. Because when you take the derivative, you have an n plus 1 coming down, and then that reduces it to tangent to the n, and that the n plus 1 cancels with that n plus 1, so you just get that, times the derivative of tangent, which is the secant squared, so that. Okay, and then to exploit this one, this would be if you had an integral of the secant to the nth power of x, but then you're also multiplied by secant x and tangent x, in addition to that. So really, if you had secant to the n plus 1, you peel one of them off, and there your integral is going to be the secant to the n plus 1 of x over n plus 1. Because when you take the derivative here, you'll have n plus 1 come down to cancel that out. So you get this. Then the derivative of the inside part will be that, and that times that will be the rest. Okay. So you want to get this into a situation where you can either exploit this formula or the other one. Okay, and then there's this thing that might be helpful in doing it. Okay, for this particular case, we can solve this for tangent squared. That's going to be secant squared x minus 1. Okay, so this gets replaced with secant squared x minus 1, which is going to be 9 secant squared x minus 9. And then here, we really have this situation here, but really with the n equal to 0, because this is just not there. And so this is just going to be 9 tangent x when you take the derivative, when you take the integral, I'm sorry, minus 9x, and then plus a constant. Okay, so let's do next one. Next exercise is a little bit harder in trying to figure out how to exploit it. Okay, so you have an odd power on the tangent, and you just have a plain old secant here. So you look and see if you just have a secant, I would say at this point, I think that if you have an odd power here, then you're going to go with this one. And if you have an even power on the secant, you go with this one. I would say that probably would be safe to bet right there. So an odd power on the secant, go with that. Even power on the secant here, you try to exploit this one. Okay, so that being an odd power there, I'm going to, wait a second. Yeah, that being the case, I think that, oh, wait a minute. No, I don't, what I said doesn't make any sense. Ignore everything I just said. And let's see here. The derivative of the secant is secant tangent. So, or maybe what I said does make sense. I just lost my train of thought. Okay, so anyways, for this particular case, what you can do is if you rewrite the tangent cubed as tangent squared times tangent x, okay, and then of course you still have the secant x there, then this is like that, okay? But we have this tangent squared, so if this were secant, then everything would be great. We'd be able to take the integral, but it's not. But it's okay. We can use this formula here. And plug it into here. So now everything here is secant, and so then we can exploit this one here. Okay, so we have 8 secant squared x tangent x secant x. So we keep those separately. We don't combine them. And then we have minus 8 times negative 1. 8 is minus 8 tangent x secant x dx. Okay, so great. So now we exploit this one. So we have secant squared, so that becomes secant cubed over 3. So the integral, so if you take the derivative here, you're going to get exactly what's inside there. Here, likewise, this is just going to be secant x plus a constant. Okay, so you're gonna get this. Okay, any questions or concerns about this one? Okay, let's move to number 5. Okay, so here we have tangent cubed times secant to the 6th. In this case, we have an even power on the secant. So we'll try to exploit this one. We'll need a secant squared on the end. Okay, so this secant to the 6th, we'll split that up into secant squared, secant squared, secant squared. Okay, so we just split that up into those 3 pieces, and then the secant squared x is tangent squared plus 1. This one you leave alone. You leave it as secant squared because you need it here. Okay, this one you need it for here. Okay, that's that part. So you leave it as, you don't change it, because if you have everything in tangents, then you're not going to be able to do anything. Okay, great. So now, and then let me multiply these 2 together. So that's going to be tangent to the 4th of x plus 2 tangent squared x plus 1. And then we'll distribute that in, and we're going to have tangent to the 7th of x secant squared x plus integral of 2 tangent this is tangent squared, and that's, so it's going to be to the 5th. Plus, and then you have tangent cubed. Okay, again, this is the g prime of x when you're looking at the chain rule. This is the derivative of the inner function right there. And the inner function is tangent in each of these cases. The derivative of tangent is secant squared. So this is going to be tangent to the 8th of x over 8. This is going to be tangent to the 6th of x over, well, it would be over 6, but there's this 2 here, so we'll put over 3. And that will work, because when you take the derivative, the 6 will come down. 6 divided by 3 is 2. And then the derivative of tangent is secant squared. And then this last one, it'll be tangent to the 4th of x over 4. And then, of course, you have plus the constant. Okay, any questions or concerns about that one? And then finally, let's move on to the last one. This is the third type of problem, and I only have one of these here. And this is where you have 8x and a 5x. You have different sine 8x and cosine 5x. So those are the 8x and the 5x. It makes it so none of the previous things really work. And this is one thing that you have to watch out for. If they're not, like, if they're both 2x, or they're both just x, or they're both t's or whatever, then it's much easier. But if they're different, then it kind of, you can't like mix them together. And then the derivative of this one has nothing to do with cosine 5x. The derivative of sine x is cosine 8x, which is like, it doesn't really mix that well with cosine 5x. Okay, but anyways, you have these formulas here. Since we have a sine and a cosine, then for this particular problem, we are going to use this formula here. Okay, so it's going to be 7/2, and then A is 8x and B is 5x from here. So the A is 8x, the B is 5x, and so you're going to have sine of A, which is 8x minus 5x, plus sine of A plus B, 8x plus 5x. So that's sine of 3x plus sine of 13x. Okay, so you take the integral of that. Cosine 3x will do it to you, but when you take the derivative here, you'll have a negative come out, which, so I put a negative right there to cancel that off. And you also have a 3 come out because by the chain rule. So when that 3 comes out, it'll cancel with that 3. And then likewise here, this will be cosine 13x, but you'll have a 13 come out when you apply the chain rule. So, and then plus a constant. So this is going to be -7. So distribute the 7/2 in. Wait, what am I doing? -7 cosine 13x over 26 plus a constant.